Welcome back. In this module, I'm going to go through the cerebellum, basal ganglia, frontal lobe connection, and this is going to be a building process. And what I mean by that is this. I want to introduce this idea of how this works and how these loops and how these networks work and function and bring about so many different things. But then I'm going to actually do specific videos, individual videos on the cerebellum by itself, giving more information about that, as well as showing you history and physical exam findings that you're going to find. I'll do the same for basal ganglia and frontal lobe as well. So let's just jump right in here. First, I love this this slide right here. I've seen this up here before, effects, and I've even used it before in other boot camps, effects of atlas misalignment. Not all of these, but most of these can actually be attributed to what we're going to go through in this cerebellum, basal ganglia, frontal lobe connection. So let's talk about it. First, let's talk about in here of the cerebellum. The cerebellum, which is this guy right here, the cerebellum, as amazing as it may sound, has more neurons, has more brain cells. You have more brain cells in your cerebellum than you'd have in the entire cortex. So the cerebellum is a major player in what's going on in the function of the brain and the function of the body. And I think the first point to catch that I think is really critical to understand, and I don't like to use the word critical, but I'm just put an asterisk and say very important to understand, and that's this. The cerebellar is the conductor. The cerebellar is largely the conductor of the brain. It's the conductor of what's happening through the motor system of the body. Now, the cerebellum is not necessarily executing and making things happen, but what it does to a large degree is to say, hey, that's cool, that's working, now let's make it better. So I'll give you an example. You know, you start to learn to ride a bike, or you start to learn to ride a skateboard, or you start to play racquetball, or you start to do ping pong, or you do whatever activity you're doing. When you first start doing it, or this is a big great one, how about knee chest adjusting? You start doing it, and over time there's this innate thing that happens. You make the adjustment, you know what desire you want to have to make that adjustment come out right, and your cerebellum saying, okay, cool, I like that motivation, now let me show you how to do it better, let's package it, let's make it better, let's make it better. It is definitely the people that are your top athletes in the world are people who have very highly developed cerebellum. You take people who ride skateboards for a living and some of the crazy stuff they do, and you see in the Olympics, some of those, you know, skaters and some of the skiers and the different things like that, you're going to see people with very, very, very highly developed cerebellums. So let's talk about how this really works. Yesterday we described, not yesterday, I'm sorry, but the first video we actually talked about, and I cut it yesterday, but in the first video we talked about the mechanisms of what's happening with the upper cervical subluxation. And one of the things we outlined in there that I thought was really important, I just want to review just very briefly and say that the cerebral spinal fluid bathes the brain and allows that brain to be buoyant. In other words, you're going to have 30 times less feel like weight in the brain, so much, much, much less, whoops, you're going to have much less gravity stress. And as I said yesterday, gravity really is one of the #1 issues that can cause stress and strain, if you will, on particularly the base of the brain, because it's catching the brunt of it. And the cerebellum perhaps can even suffer even more of that. So when we look at this right here, here is the cerebellum. We have the cerebellum right here. But let's keep in mind that the cerebellum is getting inputs from many different places. It's getting inputs from proprioception. We talked a little bit about this yesterday, but I keep on saying yesterday, but proprioception coming from your feet touching the ground, proprioception from your core muscles, proprioception from C1 and C2, the joints and their alignment. Proprioception is feeding heavily into the cerebellum. Also what's coming from your eyes, what's coming from your otoliths, your semicircular canals in your ears. That's feeding into the cerebellum. But not only that, but all parts of the brain are feeding into the cerebellum on a continual basis. And so that and we think of it like this, we think of the cerebellum, it has to do with fine motor movement. It really does, but it's actually deeper than that. It's not just fine motor movement. What it really is, if I can articulate this well, I would say that fine motor movement is just one more expression of the cerebellum saying, hey, let's do that better. So you could have cognition, how you're thinking, your cerebellum say, hey, let's do that better. You could have emotions, you could have your autonomics, you could have different various functions in the body, the cerebellum saying, let's do it better. So how does this all work? How do we tie in the basal ganglia, and how do we tie in the frontal lobe? Well, let's talk about this just a little bit. The cerebellum sits down here. It's the conductor, okay? And it's what, as I said, it doesn't execute the movement, but it tries to make all movement. And by the way, cognition is considered movement. Cognition is considered movement, and anything that's happening up here in this frontal part of the brain has to do with movement. This is the movement we understand traditionally as movement, your arms, your legs, your body moving, but also cognition, thoughts, different things like this are considered, everything out of here is considered motor movement coming out of that frontal lobe, and that's of course where we have our cognition. Even social behaviors and different things like that come. And so, but anyway, going back to what I was saying is that the cerebellum isn't executing the movement. What it's doing is it's fine-tuning the movement all the time. Now the basal ganglia, it's very interesting. What does the basal ganglia do? If you were to ask me, okay, what is the function of the basal ganglia? One thing I would say, in a very general term, is I'd say the basal ganglia largely serves as the on-off switch. So the basal ganglia is going to either turn things on or turn things off. So in other words, if you're going to have movement, then movement starts in the frontal lobe. When you have movement that's starting in the frontal lobe, it's going to go down to the basal ganglia, and the basal ganglia is going to say, oh cool, that's awesome, let's turn on and let's activate, let's move. So it feeds back through the thalamus and goes to the cortex, and then helps that movement become more fluid. It increases the amplitude of that movement, and it just makes that movement work better. The next thing that happens is that that impression of what kind of movement. Let's just say it's an arm movement, just to make it simple. You're moving your left arm. Okay, start from the beginning. Right here in this part of your cortex, you're going to say this is where your executive function takes place. It's called the dorsal lateral prefrontal cortex. Dorsal lateral prefrontal cortex. Don't get hung up on that right now. We're going to talk about that later, so don't get hung up on that. But the dorsal lateral prefrontal cortex say, okay, I want to move my arm. It's going to go over here to what's called the premotor area, which is the planning area. Then it's going to go to here. Remember the homunculus man? Homunculus man's going to start the move. Well, as it starts to move, almost simultaneous, it's going to send a message down to the basal ganglia. The basal ganglia is going to say, let's turn on. It does that by going to the thalamus. Thalamus goes up here and further activates what's going in that motor function. Now, at the same time, almost simultaneous, so that's one loop. This loop is happening right here. That's a loop. The next thing that's happening is that part of the frontal lobe comes down. It's not only going through the corticospinal tract of the arm, but it's also shunting over to the pons, and then the pons goes to the cerebellum, and the cerebellum says, okay, I see that movement right here. Now, let's make it better. So then we have this loop that's going on. So let me, if I can keep this from being too confusing, let me erase everything here, and let me just say it very simply one more time. We're going to move the left arm. I'm just saying left arm, it could be anything, right? So this is going to be the right cortex right here, because the right side controls the left side of the body, right side of the brain, right? So right here in our dorsal lateral prefrontal cortex, we say, okay, let's move. That goes to what's called the premotor area, of the frontal lobe, and then that's where you plan the movement, and then that backs up one step and goes to the motor area of the frontal cortex, and then you start to conduct the movement. Now, as you are conducting the movement, you're going to have a loop. You're going to have two main loops. You're going to have a loop that goes to the basal ganglia. Basal ganglia is going to say, that's cool, let's turn it on. Basal ganglia is going to go to the thalamus. The thalamus is going to further accentuate the movement effort that's going on in that motor lobe. I'm sorry, in the frontal lobe coming from that motor cortex right there. So at the same time that this is happening, the cortex is also speaking to the pons, goes to the cerebellum, then the cerebellum says, cool, I like that movement, that's great, let's make it even more coordinated. Let's make it a finer movement. Let's orchestrate it. And so it comes back up through here, through the thalamus, and back to the frontal lobe. So we have this loop going from the frontal lobe to the basal ganglia, thalamus, frontal lobe. And we have this loop going this way. And then on top of that, we've got the basal ganglia and the cerebellum coordinating with each other. So I know that sounds confusing, but basically, if you can think of it like this, the frontal lobe initiates the movement, and the basal ganglia gives it the juice to move, and the cerebellum gives it the coordination to do it properly. So we said with the left arm here, if we're doing the left arm, we're going to have the right frontal cortex, we're going to have the right basal ganglia, and we'll have the left cerebellum. So the cerebellum acts largely ipsilateral, where the basal ganglia and the frontal lobe work contralateral. So just to get the basic concept down, and this is the way we want to think about it when we're doing our upper cervical work, we're not going in as a functional neurologist and trying to know all the intricacies of each one of these individual loops, because there's actually can be hundreds of little bitty minor loops that come off that. It can become crazy and insane. But the most important loop that's going on is what I have described here. These two loops largely work together. Okay, so now we're going to talk about that just a little bit more, but first let me lay just a little more foundation. Okay, this is a building process as I'm talking about. In humans, the cerebellum plays an important role in motor control, and it may also be involved in some cognitive functions such as attention and language, as well as regulating fear and pleasure responses. But its movement-related functions are the most solidly established. The human cerebellum does not initiate movement, that's what we talked about a while ago, but contributes to coordination, precision, and accurate timing. And guess what? Sometimes bad cognition is just simply bad timing that's coming from the cerebellum. It receives input from sensory systems of the spinal cord and from other parts of the brain and integrates these inputs to fine-tune motor activity. Cerebellar damage produces disorders in fine movement, equilibrium, posture, motor learning in humans, also learning, cognition, and language, and emotions, and different things like that as well. So it's pretty easily or pretty well accepted that cerebellum helps provide smooth, coordinated body movements. But the point I really wanted to make with this is when we're talking about overall brain function, your ability to have cognition, your ability to even have memory, your ability to coordinate thoughts in your brain can have a lot of impact from a malfunctioning cerebellum, because keep in mind the cerebellum is the conductor, and it is making sure that everything that happens that you're involved with, whether it's going on in your brain or whether it's going on in your body, what your cerebellum is trying to do is make it awesome. It's trying to continually refine and make it better and make it better and make it better. Very interesting. You've probably heard the stories that you could have, they've done the experiment, and I don't have it's just off the top of my head, and I don't have the actual research in front of me, but they've done experiments in playing basketball, and what they found and I've heard these studies, that they would have a certain group of kids going out shooting free throws. And then they would have kids sitting on the bench for extended periods of time over, it wasn't over a day, but larger periods of time than that. And they would visualize shooting free throws and making the perfect free throw, making the perfect free throw. And at the end of the day, at the end of the study, the people who sat in the bleachers and visualized the perfect free throw and making the free throw at the end of this study, at the end of their program, actually improved significantly more than the people who were actually shooting free throws. So there's a lot going on here, and so even thought itself. So how is that fine motor movement getting better with the people who are simply visualizing making free throws as opposed to the ones that actually are using their muscles to do it? How's that happening? Because there's a lot more going on in the cerebellum than just simply fine motor movement. It has to do with cognition. It has to do with all these other various aspects. And I will tell you something else that's very, very important. And when we get into the cerebellum, I'll talk a little bit more about this, but there's something else that we really need to discuss and put in here, and that's this. Let's look at the brain here. Here's the brain. Here's the nose and the mouth. So we're looking from the side. Here's the brain stem. Here's the spinal cord. Here's our cerebellum. Okay? And here's the atlas right there. So when you look at this, one of the things that the cerebellum does is gives you balance and gives you equilibrium, if you will. Okay, so equilibrium. And it's keeping you upright. Well, it's very interesting because from a standpoint of understanding brain development, child development, and so on and so forth, as the baby is born, you notice that they can't even hold their head up. They have no postural control. There's nothing going on in the midline, you know, the spinal postural control. As they begin to develop, they begin to hold their head where they're not flopping around. Then the first thing you know, you can raise their head up and they start looking up. Well, what's happening there is the middle part, the midline of the body is beginning to get a little strength. Well, guess what? That absolutely perfectly coincides with this. I'm going to take this cerebellum here and I'm going to look at it from A to P. I'm looking lateral here, but I'm going to look A to P here on this cerebellum. And that is probably about the worst cerebellum I've ever seen. So let me try that again. All right. I tried to get too fancy with that, but let's don't get fancy. Let's just do the cerebellum like this. Okay? So what we see when the babies begin their development and their postural control starts to come online, we see the midline or the middle part of the cerebellum begin to develop. Now, the next thing you're going to notice is they still have no hand control. They still have no hip or shoulder control. They're flopping all over the place. But the next thing that happens, they get into about 6 months old, and then all of a sudden, 6 to 8 months old, they can start sitting up by themselves. Well, what's happening there? Well, now the hips are beginning to engage, and they can start moving their shoulders in gross movements. They still can't do their fingers at all. I mean, they'll flop them around, they stick them in their mouth, but they're not really, they don't have any coordinated fine motor movement that's going there, but that they are beginning to get strength in the hips and the shoulders. Guess what's happening there? That's when the intermittent cerebellum is developing. Yes, that's exactly what I'm saying. The development of a child can be seen in the cerebellum. Now, as they get up and walk, you'll actually notice when they walk, I wish I could demonstrate this, but I'm, on the webinar here, or we're doing this through the video. And so as they begin to walk, they're walking and they're kind of stumbling around, but their arms are kind of flailing all over the place. Their hands are flailing all over the place. And at that time, they can't take a round peg and put it in a round hole, or a square peg in a square hole, because they don't have the fine motor control. But about the time that they begin to talk, and about the time that when they're walking, their hands start having a normal arm swing. This is about the time, that lateral cerebellum begins filling in. Now, Why do I bring this up? Because if you look at animals that have a lesser developed cerebral cortex, which is the majority, they do not have this development in the lateral lobe of the cerebellum. And some things like there are certain fish and certain things like that that all they have is a midline. And then you go up to other animals and you'll see they actually have the intermittent, but you'll see very few that have the lateral. As a matter of fact, humans really have the market on that, because as you have the lateral, what happens is it causes something called lateralization of the brain. So you get lateralization of the brain. When you get lateralization of the brain, that's when we start really developing higher orders of things like executive function, being able to make decisions, social behaviors, different things like that come from that lateralization. Now, why am I saying all this? Because everything is predicated upon the development of what's going on in the brainstem and the cerebellum. Let me check this out. This is really important. The cerebellum and the brainstem is what largely develops the brain. The brain itself is developed from a child neurological standpoint, is developed from this way. The brainstem and the cerebellum are driving the development of these of the rest of the cortex. And as we grow this cerebellum from the midline, I so apologize, my thing's done. As we go from the midline of this, I'm trying to go right here. As we go from the midline out this direction right here, as we move this way, think of the brain growing out from that brainstem and actually filling out laterally. And as you fill out laterally, we become more executive thinkers. We become more socially acceptable. We become more of all these things that we know as being human and being alive and being what we are. Now, as we look at this, from this standpoint, the cerebellum becomes very, very integral in its importance in being able to be the conductor of what's going on with the brain. Okay, so let's look at this right here. We see this is a depiction I thought was kind of nice right here. We've got the left cerebellum here is going to communicate with the right brain. We talked about that, how this is the ipsi and that's contra to the body. Right is going to drive the left brain. So if you have normal output from the cerebellum, it equals normal nerve input to the frontal lobe of the brain. Now, if you have normal input to the brain, now the brain can come back down and talk to the brain stem down through the body. This is an important point to catch right here. Here's another very important bullet point for you right here. The mesencephalon, another word for that would be simply the midbrain. The midbrain is largely your sympathetic nervous system. Your midbrain is what drives the sympathetic nervous system. Your pons and your medulla largely drive the parasympathetic nervous system. Okay, so check this out. So when the cerebellum is given the juice to the brain comes back down here, gives the juice to the pons and medulla, goes down to the body, everybody's happy, and we have a balanced autonomic nervous system. Now, but what can happen is if the cerebellum is not functioning properly and it does not give the normal output into the brain, then when the brain comes down this way, it does not give the normal output to the pons and the medulla. And when that happens, we are going to have some imbalance in the autonomic nervous system. And as I talked yesterday about the pathophysiology, neurophysiology that's going on as a result of an upper cervical subluxation, the detrimental effects that the subluxation can have on the cerebellar function very well can play into this very mechanism and cause imbalances in the autonomic nervous system. So here's just another place to depict it. The cerebellum is driving that frontal lobe right there. And decreased This is from this picture right here. So let's say we have decreased right cerebellum into the left brain. Now the left brain isn't giving the juice down to the pons and medulla. And in this depiction is showing that this is causing you to be a sympathetic dominant. So now the mesencephalon's overfiring. What are some of the things that you're going to see when the mesencephalon's overfiring? Well, one of the things you're going to see are things like pupils are large, digestion is bad. You're going to see all the things that, your adrenals are wearing down. You're going to see a whole bunch of stuff that happens, and negatively, and we're going to talk more about this more specifically in upcoming videos, so I don't want to go too far into that. I just wanted to share that when this guy starts burning hot, you can expect anything to come down. Let's just get down to it. This right here is a major factor in the causation of dis-ease. And dis-ease over time, give it long enough, and you can name it whatever you want to name it, whatever it becomes, whatever it manifests in, because as B.J. Palmer talked about, dis-ease, lack of ease, when you have that midbrain or that mesencephalon overfiring, you can really have problems. Okay, so going back to this, the cerebellum, as I said, is the conductor. The frontal lobe right here is the initiator of movement, whether that's cognition or what we know traditionally as movement. Sitting right about here is the basal ganglia, and so the basal ganglia is the on-off switch, and the cerebellum is the coordinator. There's something I did not mention a while ago that I need to mention, and that's this. The basal ganglia is the on-off switch. If your on switch is not turning on, then this looks like things like Parkinson's, which we are going to detail in future videos. If your off switch is not turning off, this looks like things like OCD. This looks like tics. OCD looks like, those obsessive addictions, different things like that. So okay, so coming back to this, I think we've already discussed this. I think that's pretty good to go. Basal ganglia, we're going to do a whole video on basal ganglia to root that out. We're not going to get way into the depths of that, but I just want you to understand basic mechanisms of how it works, and most importantly, I want to outline how you can examine it so you can see when you do your upper cervical work improvement in that basal ganglia. So frontal lobe, of course, we have planning, goal setting, motivation, attention, reward, impulse control, judgment, movement. All of these things can be knocked off if that cerebellum, basal ganglia, frontal lobe, if those loops are not working properly, and especially if you have an upper cervical subluxation that's causing the cerebellum to be the weak link in the chain, you can actually see any one of these, and that's what we want to learn through this upper cervical boot camp. How do we examine that, and how do we know that? Because here, when it comes down to it, I just had a patient come in today. It's very interesting. 22-year-old male. And he came in, he's just finishing up college, he has one more semester. He says, man, I have a lot of focus and concentration problems. Well, what I did was I did some basic cerebellum exam, like I'm going to teach you, examination, and I did a basic frontal lobe examination and a basic basal ganglia examination. And when you have problems with concentration, or if you have problems with attention and focus, it's coming out of the frontal lobe. That's a frontal lobe function that's not working properly. But it doesn't mean that the cause of it's the frontal lobe. It just means that that's something that's manifesting out of the frontal lobe. So after doing the examination, he did great on frontal lobe exam. He did great on basal ganglia exam. His cerebellum was toast. It wasn't working very well. And I was able to explain to him. I said, look, the cerebellum's not working well. I think that there's a good possibility that your head position has something to do with that cerebellum not functioning properly, and that very well could be what's driving that focus and attention. and I'm pretty sure it is. So he's gonna do really well. But it was nice for me to be able to just take a few minutes and show him exactly what's going on. And his mom was like, "Whoa, how did you know that?" You know, so it was a pretty cool experience with him. Okay, so just a couple more things I want to go over, and then we're going to end this video. The frontal lobe has many different functions, which we're going to line in the next video. But keep in mind, and I need to skip ahead one, keep in mind right here that the left cerebellum is actually going to drive the right cortex, frontal lobe, the right brain, if you will, and the right cerebellum is going to drive the left. So when we have people who have weak cerebellums on the, let's say on the left side, a weak cerebellum on the left side, you may find some of these things actually come about. You might find that they have like facial recognition comes out of that right side of the brain. You might find that they don't do as well with facial recognition, but they remember names really well. You might find that they are even things like they have a lot of fear, you know, because the right side of the brain is more the fear side. You might find you know, they don't appreciate art. You might find their creativity, imagination's down there, intuition, all these different things. And conversely, if somebody has a right cerebellum, sometimes you'll find that they have problems with language, or they have problems with logic, or they have problems you know, remembering names, or they have problems with different things. You'll see some correlations like that, for which we're going to be talking about. So it's pretty cool. I mean, when we look at it, the brain as it sits here, of course, we've talked quite a bit right now about the frontal lobe, but you know, the parietal lobe has a lot of different functions in it too. Things like one of the things that we'll see that's in the parietal lobe is something down here called Wernicke's area, and that's where you understand the spoken word. And then up here is Broca's area, and that's how you know how to use your muscles in your mouth to actually verbalize. So sometimes people's speech problems come because they can't quite understand what people are saying. Temporal lobe, of course, we think about hearing with temporal lobe, but also you think about in here you got the hippocampus and other issues. You have memory problems and so on and so forth. And occipital lobe, you're going to see a lot of things with visual and so on and so forth. Also, parietal lobe, spatial awareness and so on and so forth. All these things have to be coordinated, and they feed into the cerebellum, and then we have our loops here. The cerebellar networks with the cerebellar cortex and basal ganglia. The dominant view of cerebellar function has been that it is exclusively concerned with motor control and coordination. Recent findings from neuroanatomical, behavioral, and imaging studies have profoundly changed this view. Neuroanatomical studies using virus transneural tracers have demonstrated the cerebellar output reaches vast areas of the neocortex, including regions of the prefrontal and the posterior parietal cortex. Furthermore, it has recently become clear that the cerebellum is reciprocally connected with the basal ganglia, which suggests that the two subcortical under the cortex structures are part of the densely interconnected network. Taken together, these findings elucidate the neuroanatomical substrate for cerebellar involvement in non-motor functions mediated by prefrontal and posterior parietal cortex, as well as in the process of tradition associated with the basal ganglia. So here we go. Here's the wrap-up. The basal ganglia, these structures largely fulfill the on and off switch. It gives the brain the juice or the brakes, whatever's needed for the given situation. The front, and I said the frontal lobe. The frontal lobe is where movement comes from, whether it's cognition or what we traditionally understand as movement. The cerebellum is the conductor. It's taking everything it gets and say, let's make it better, let's repackage it, let's make it better, let's repackage it, let's make it better. Just to reiterate one more thing before we close this section, yesterday we talked about, in light of what we've just discussed right here, if you look at that cerebellum right there, you see how this is the foramen magnum here? You see how those cerebellar tonsils are going down? Do you think that that's healthy for that cerebellum? The point behind this upper cervical neuro boot camp is basically this. Can we do a history and can we do a physical exam that will show us a cerebellum, a basal ganglia, a frontal lobe that's not working right? And can we do our upper cervical work and turn around and through videos and pictures or whatever we want to, whatever media we want to use, can we show the patient and ourselves and the world or whoever wants to see that after I applied my upper cervical work, that I have shown improvement in these functions, therefore I've shown improvement in the brain, therefore I've shown improvement throughout the entire system, neurologically, physiologically, and all ways.